Good afternoon, all. I hope you all doing well. Uh, I request please inform your colleagues or friends to join the session. We have very less participate. That is just a 48. So we'll wait for 4 more minutes. We'll start at 3:10. So I request please inform your colleagues to join the session as soon as possible. Okay, we will start. Good afternoon, Vipul sir.
Yeah, good afternoon, everyone. So, okay, let's start. So, yesterday we were talking about some algorithm, that is Deuce algorithm. So, they have given the quantum method. They've applied the quantum method in finding the basic thing like the function is constant or not, or is a balanced function. So he has only proved this quantum supremacy over this from this problem. So now we are moving towards the next algorithm, that is Shor's algorithm. So let me share this PPT. 1 minute. Hmm. Hmm. So yes, so now we are moving ahead for the Shor's algorithm. Actually, the Shor's algorithm, it's actually he has tackled one problem. That problem is called factorization problem in our computer field or math field also. So what is the factorization problem? So first I want to emphasize, so I'm tackling this algorithm in a different way, that I know that the same things and all whatever is happening in the Shor's algorithm and all of the quantum computing course, I'm just focusing on the what is the basic problem in that, because I just this is my belief that go on the basic problem, only then root of the problem, only then we can understand the importance and all that. So I'm just basically emphasizing the what is the basic problem of the Shor's algorithm. Okay. The Shor's algorithm first deal with the factor problem. First, we have to understand this deals with the factor problem. Now, what is the factor problem? No, everybody knows actually. This approach of mine, what I am presenting at here, this approach and method actually based on my previous 5 year experience, whatever I am dealing with my interns, whatever I am dealing with my colleagues, and what I am dealing with my most of the quantum computing teachers, right? So based on that, what I found that there is only and only 30, 30, 40, 30 to 40% teachers who are dealing with the basic problems. And rest of them, whatever the interns are there, teachers are there, they are just tackling this as a uh, only this, the what are the main steps written on the Shor's algorithm, only they are doing like that. Okay. So, in whatever is in industry, you are basically prone to find or to manipulate the things from the very initial level. So, so I just from that thought, I just originated this approach. So, what I want to emphasize here, that what is the factoring problem? The basic factoring problem, I'm starting from here, that large numbers are hard to factor. So why hard to factor? That this is a very basic thing. Everybody knows that if multiplication of any number, we will finding the output very easily. And actually, we have to see all these things from the two point of view. First, from the mathematics point of view, and a second from the our computer point of view. That is, computer point of view means algorithm point of view. And computer problem point of view means one of the meaning is that we have to also see the keep in mind that capacity of a computer. That is deal with the, I think most of you are knowing that capacity is dealing with the complexity problem, that is time complexity and space complexities, like that. Okay. So all these things we have to keep in mind. So what I'm telling that if you are factoring a number, suppose you are multiplying a number, that is you are 7 into 5 giving 35. Okay. So in this multiplication or in this process, this is I'm calling this a forward process. In this process, this is a forward process. If you are going to enlarge a number, going to from smaller to bigger number, suppose you are inquiring suppose 1034, and then you are inquiring 3451. This Then this multiplication is also very easy. So complexity will make no constant at here. What complexity you are multiplying with here with the same or 5% or 10% more complexity, you can multiply, or 20% more complexity, you can multiply this number. Okay, so there is no hardly a difference. As you will go, suppose you can go 100 digits number, you can also multiply this number. That's 100 digit numbers. That means 10 to power 10 or 10 to power 9 number into 10 to power 9 number. That order of this I'm saying order, not 10000 like that. Okay. The order of 10 to the power 9, you can multiply very easily and you can get the result. So there is no complexity restriction at here. That as soon as whatever the numbers we have the rule for this to multiply. We have the algorithm. What the algorithm from the computer point of view, from the algorithm point of view, what we are doing, we are making the pathway by inputting the mathematics rule. Okay, this is the basic thing of algorithm, right? What we are doing, we are just making the pathway by inputting the basic mathematical rules. Okay, and we know the mathematical rules of multiplication. Okay, there are very basic rules. There is a unit digit, tenth digit, hundred digit, like that. It's a very basic things. Okay, so that multiplication we are forming into the form of algorithm. Okay, that's no problem. Okay, but the reverse is not true. The factorization, this forward process, this I'm calling a forward process. The forward process of this this multiplication having no complexity issues. If the issue is coming, that is 5% or 10% higher than the complexities and nothing else. Okay. So large number of multiplication we can do very easily, that we are calling as a forward problem. Okay. So it makes no problem at all. Now I'm talking about the reverse problem. So what happens in the reverse problem? So the reverse problem is just like this: 35, that is 7 into 5. You have to factorize this one. Okay. And this time I am relaxing one constant, that is a prime number constant. But later on, I will include that constant also. Okay. For the sake of clarity, I'm just relaxing that constant. Okay. But later on, we will include that. That is 35. We have to factor this. So factoring, we know very easy, but for the small numbers. This we have learned in the sixth, seventh, or eighth classes. That's very easy. So no problem in that. But it's very easy as long as this number is remaining small. Okay, this number is 70. We can do factor, no problem. This number is 100. We can do problems, but no problem. Okay. But as we are increasing the amplitude of this number from 35 to 100 to 1000 to 10,000, like this, we will get involved in the complexity issues as from the point of view of classical computers. Okay, that the factoring 70 is very easy, 100 is very easy. But why very easy? Based on our observation. If we are increasing going on to 1000, it's easy based on our observation, 10 into something. Okay, but this I'm doing telling 1000. But if we will do 1076, then their factorization is something typical. So as the number will go on increasing and increasing, we have no choice of factorizing this only based on the memory recall. So memory recall means we know that 5 into 6, like that. So whatever we are having in our memory, we can recall it. Okay. So there is no single rule that can do this. Okay. Why there is not single rule? I will also emphasize these things here. So as the number grows, the factor search space exploded. That is 3-digit numbers. That is around 30 possible cracks. So we have to see the possible cracks. That is one by one inputting, and we are finding the solution for that. So on classical algorithm, we are only doing these things, okay, by for finding the factorization problem. Okay, if we are going a six-digit number, it will be around 1,000 checks, and this is approximate checks I have written here. A nine-digit number like that. So 100-digit number, if we are going, that is 10 to power this one possibilities. Okay, 1 minute. Let me zoom. Yeah. Otherwise, some other people will not able to see this. Yeah. So, as the number is going on, the possibilities, number of possibilities to find out that solutions or factors are going on. And as the number of possibilities are going on, then it means we are into the complexity issues. We have entered into the complexity issues from the classical computer point of view. What? Why? Because what the classical computer is doing, they are randomly choosing something and inputting one by one and seeing the possibilities like this. Okay. So that is, suppose suppose we are going on the 100-digit number is also a digit number that is beyond our imagination. We cannot imagine 100-digit numbers. Okay. We can imagine 10 to power of 5-digit number, 10 to power 6-digit number, 10 to power 8-digit number, or 10 to power 9-digit numbers. Even 10 to power 20-digit number we can imagine. But 10 to power 100-digit number, it's out of the imagination. Normal person cannot imagine that one. Okay. But this 248-bit or digit number, that is the RSA number, RSA different technology, uh, uh, that is having the possibilities this much. 10 to power 616 possibilities that are almost impossible. If you will take a whole universe time, even then you cannot calculate. So that means what is the classical computer do? They will do some simply they will forward this thing. Okay. So this is the problem from this factoring. But why this problem is occurring? So I'm coming on the next slide. So this is the simple data I'm representing here. It's nothing. 2048 bits. That is, bit means numbers, digit numbers. That is having this one. And because these are the things which are impossible here. These are the things which takes a very long time and very impossible, and the factorization itself is very impossible. And if we impose one restriction on the factorization, that the factors which are coming out from any number, suppose x number, is factorization is coming out y and z, then if we imposed ourselves to this restriction that both y and z should be a prime number, then it is taking a 10 to the power 616. These steps, if we are restricting further the problem of prime numbers, then it will make a more complicated problems. Okay. So so these two things, our encryptions are now utilizing this weakness of the classical computer. Okay. So what they are utilizing, they are utilizing the trick that in encryption, whatever the encryptions are running here, RSS encryptions are running here. So I have not worked on the encryptions, but some of my friends are working on the encryptions based on their given knowledge. I'm just telling this one. Then what they are telling we are taking a 500 digits number. We are taking a 500 digit number, 400 digit numbers, 400 digit number, not 500. Okay. Need to be remembered in the mind. 500 digit number. Okay. So 500 digit number means 10 to power 500, like that. Okay. So 500 digit numbers, 400 digit number at randomly they are taking, and they are just multiplying them. So 5, 4, 3, 2, 1, 7, 8, 9, like that. Go on, and just go on until 500 digits. 3, 2, 5, 6, 9, 8, 3, 5, like that. Just go on, and 400 digits. This is 500 digits. Okay. And they just randomly multiplying these numbers. So when they are multiplying this number, they are getting such a number in such a order that the factorization of that number is impossible. Why? Because the incapability of the space complexity, time and space complexity is both. So it will involve the both the problems, the time complexity always as well as the space complexities, right? So all, our encryptions are based on these techniques because this is the weakness of our classical computer. Okay, so but this weakness is our biggest strength in the finance sector, in the banking sector, UPI payment and all that. What we are encrypting, that is long digit numbers, very bulky digit numbers, and multiplying it randomly, and we know who are multiplying. They know the prime factor, but when it will be in public, so the hackers cannot know the prime factor. Because if they are going on the prime factor, it will take a years and years, billion years, right? So, uh, okay. So now I'm coming on this fact that why it is impossible to do the factors, because everybody will observe. So first time when I hear this problem, that factorization is impossible. So I was not believing the factorization is impossible because factorization is a left hand game for us. But we were wrong. When I saw these things deeply, some projects coming into my company, and we have worked on the root problems, then we have realized that yes, it is. So what it is now, I'm just emphasizing that things also. Yeah, and I have also gone through a lot of literature, lot of videos, YouTube videos when I was returning this quantum computation field. Then I found there is no such a videos, not such a things. We have to go in depth. So all these things are based on, these lights are based on that experience. So all of you can be benefited. So when I searched that why factorization has no shortcut, then I found then there is a no structure in how factors behave. When we are factorizing, okay, when we are factorizing, it was hard to believe to me that why the factorization is not being done. But yeah, it is true. Why it is true? When I go went to the depth of this, then I found there is no structure in how factors behave. There is no formula for the defined ones. That means how we have to do, no formula is being made of that. There is a formula for the multiplication, there is a formula for the root, there is a formula for everybody's, or log n or exponential, there is a formula for everything, but there is no general formula for this factorization. And when there is a no general formula for the factorization, then just think about that. Our algorithm are basically based on the formulas. We have to input something to run on the path. But here we don't have anything. What we have to input that go in that way when it will, what if and but we will involved in the loops and all the way of the algorithm. So we cannot input of our algorithm to find the factorization. Okay, so there is no structure, there is no formula, no clear periodicity in the composite numbers, no algebraic rules that predict the factor. There is no algebraic rule. I will clear from upcoming examples. So that means we cannot guess compute that this very quickly. Okay, so we can try only possibilities, that is called hit and try method. Okay, and that hit and try method leads to the very slow processing of the large factorization numbers. Okay, so so because while teaching to the students, while I'm dealing with my interns, they are always constantly asking these questions. Sir, this factorization problem is so much typical, we are not believing, and I was also not believing. Yeah, see, there is no pattern. See, suppose we have to give in a this number, this initial numbers I have taken as an example, and these initial 1, 2, 3, 4 numbers, these initial four numbers are of same range. Just emphasize on this fact that they are on the same range. So their range is 2, 3, right? So they are on the same range. This 2, 3, starting with the 2, 3. Okay. So only last digits are changed. So this is 10, this is 2, 3, 2, 9, 30. See the things. So 2 into 3 into 5 into 7 into 11. here 7 into 331 and 2329. What I found, this it's itself a prime number. It is not divisible by anything. I have tried. Maybe I may be wrong. I have not tried so much, but I have tried. The 2329 was undivisible, undivisible. So in which is undivisible, which is divisible by itself one, and itself that is called a prime number. So I written here a prime number. So the factorized one are 2, 3, 5, 7, 11. So see the pattern here. See the pattern here. There is a pattern, there is no pattern. Doesn't have the factorization. See the pattern here. So we can't find any one method or any one pattern following here. See, these all are factorization, all are of smaller numbers. These factorization having a one bigger number, two smaller numbers. This is one bigger number, one smaller number. Abruptly, at randomly it's coming. Okay. So so all the smalls, all smalls. One small, one big. Two small, one big. There is nothing. Although all the numbers are having the same range. And see here also, all the numbers having the same range. When all the numbers having same range, now here, this 231087. So sometimes it's coming to 1087, sometimes it's factorization coming to this one, 6667. Sometime in a two factorization, 5003 into 2. Same order. See the order of this 5003. This is 6667. So it is having same order approximately, but the factorization coming like this. Factorization coming like this. So you cannot find. Okay. So PPT, I think we will provide the PPTs. So you will access this. So just have a look on that after the 5 p.m. So and just follow the pattern. So I don't think so. I didn't observe any pattern in it. Okay. So this is the real thing. So that we are not having any pattern. If there would be any pattern, then we have the input to feed to the our algorithm. If we are having any sequence, then we will have the input to feed our algorithm. But there is no sequence, no pattern, no formula. So we don't have anything to input to our algorithm. And when we don't have anything to input our algorithm, then what we have to do, there is a one choice, there is a hit and trial method. So for a hit and trial method, so we can also manipulate in the hit and trial methods. So what we can manipulate, there is a one thing that suppose there is a lock, or there is suppose there are seven locks, eight locks there. There is a one key. So this is also a problem hit and trial. What we have to do, we have to first method we can see putting every key in every lock like this. This is the first method, right? But this involves a very much complexity. It's a very biggest. This is the worst case, omega worst, right? Okay, mu omega worst case. Then what we can do? We can do one thing, that instead of applying every year, we can leave out two and two. Suppose after this we can apply here. After this we can apply here. Although this method is a it's a hit and trial, but it will increase the chances. So suppose in a first cycle, if we are getting in these things, then there is no need to run another cycles. On the second cycle, if we are getting, then we need to run only three steps, one, two, and three. And suppose in the second cycle we are getting, then four and five, like that. So there are four or five steps only. So cut to cut, there will be there are solutions, but the solutions are revolving around the hit and try. So we can reduce the hit and trial, but not on the same considerable order reduction we can find it. Okay. So that reduction will also comprises the hit and trial methodology. So this is the actual real problem. And yes. So till now, what we are doing in the classical method of factorization, we are doing with the four, we are left with the four methods. The trial division method that everybody knows, that is check up to number of root n, that will be the upper complexity. Okay, but it will give a very slow things. Okay, but hidden trial obviously work for the very small cases, right? So there is another method which is given by this Parrot row method. Row means row means like this. So in this method, what we are doing, the same thing. We are lefting two and then trying. So like that, somebody has told us that okay, do this thing, do the this path like this, go like this path in the method. Okay, so this is the random cycle. So this is also a random cycle. So we can find or we cannot find in a one or two or five cycles like that. But yeah, this is also a classical algorithm method. Somewhere from IT field has also suggested this. Okay, algorithm. Another methods, what is yes. So another quadratic sieves. Quadratic is nothing, just make a bunch of fours. That is called quadratic. Then, but again, this is a hit and trial method. Okay, so it can go. Yeah, there is one thing because we are making a bunch, so that means it can go up to 100 to 120 digit numbers. Yeah, we can try these numbers. Okay, this is a classically. So classically, we can go on that, but this requires also the extra space complexity, but it is not impossible. Okay. Yeah, it will give the solution. So it will forward in the impossibilities up to the 100 to 120 digit numbers. So in the number field, there is another method. This is the latest method we are applying here in the classical algorithm nowadays. Okay. So IT software engineers, they are applying all these things algorithm. Okay. So in this algorithm, we still there is a restriction. We can increase the speed here, but it can also cannot find the factors up to 2000 for 2000 bits or order. Okay, so these are the four methods we are having of the algorithm till date. Okay, so but we have to find Shore has understand this problem, and of course after the Shore, these two new algorithm, classical algorithm came, but Shore has identified this problem in very earlier, and what solution they have given. So yeah, so what the solution they have given? Okay, so they have given the solution that do not scratch the factors. Right. Okay. Very good. Yes. So we don't have to go for the factors. So what they have suggested, it's a very important. That's very important. What they have suggested, they have suggested that find a periodic function. Okay. From the mathematical point of view, it is also a magical thing. From the computer point of view, it is also a magical thing. Why? Because that periodic function, to find out the periodic function very easily in a one step, the quantum computation was doing. Okay. So what Shor suggested, that just involve the periodicity, just involve the periodic function here, just make the periodic function. That function they have taken, it's a very important one. See there, what the Shor has given. Shor has said first that don't convert this factoring problem as it is to the factor. No, don't go as it is. Okay, don't go. So he's saying rather than the factoring problem, just convert this problem into the periodicity problem. Periodic problem. So periodicity problem is choose the function which is having a some period. So you have to choose a function which is having some period. Some period means it is repeating after some inputting of x values. Okay. So naturally we are choosing a function fx. That means when we are choosing a function fx, then it means it itself says that this function value is different for different x. For x1, its function value is f1. For x2, function value of f2, like that, like xn, function value of fn, right? So he's saying choose a such type of function who are periodic, right? So who are having the periodicity. Okay. So periodicity means after certain x2, x3, x4, x5, and x6, suppose after a 9, after a certain step, after certain values, this function will give you a same f1 value. So when it will give you a same f1 value, that means this 9 values, after the 9 values, we are having the same returning of that function. So the periodicity of the function will be 9 here. There is a 9 steps we have taken, 9 values we have taken. That means the periodicity will be called as a 9 here. Okay. So what is the idea of the shore? The shore's idea was to take such type of function who are having a periodic things. Okay. Okay. So that was the first idea. Now, okay, he's saying just by saying that just take the periodic function, the matter will be solved. So the answer is no. Okay. So the student can ask, yeah, yes, sir, periodic functions are very much. So there are large periodic functions in the world. So what the periodic functions are? Very first periodic function we know, sin x, we know cos x, we know tan x. All that trigonometric functions are periodic because they are repeating after a certain interval time. The square wave function is also periodic, like that. Okay. So there are lot of things for the periodic functions. Okay. But can any periodic function will work here? So the answer is no. So there is a one restriction for that. No, any periodic function will not work here. Okay. So what restriction is there? So the restriction is there that we have to take such periodic function. We have to take such periodic function whose periodicity. Suppose now we are supposing a parameter r. R is the periodicity of the function because in the previous example we have taken the periodicity of 9. Now we are supposing in a general we are supposing the periodicity is r, right? So we have to take such a periodicity, such a function whose periodicity r is depend on r depends on what number we have to factorize. Suppose we have to factorize the number n, right? So we have to choose such a function that whose periodicity depends on n. So as the number will change, the periodicity will change. Okay. So we have to take such a number whose periodicity is depending on the n, right? So see, I have seen the Shore's original paper. From that original paper, I was able to extract all these things. Okay. So and why I have gone in this type of basic things because I was not able to answer most of the interns. I was not able to answer most of the teachers. Teachers are also asking to us that when they are coming to collaboration. So, so that periodicity, we have to take such a periodic function whose periodicity itself depends on of our number n. So that means we can say in another statement, we can say that r should be a function of n. Okay. To elaborate more, uh, we can take one example. Suppose sin x. So the periodicity of the sin x everybody knows the periodicity of the sin x. This is 0, this is pi, this is 2 pi. So the periodicity of the function sin x is always a constant that is 2 pi. Okay. So periodicity of the periodic function cos x, it is also at 2 pi. Tan x, it should also be a some value. I'm not reminding. Yeah, but I am reminding this fact. All these trigonometrical functions or square wave functions, all that wave functions are having a periodicity, which is either having a constant or if not constant, then they are not depending on the n function, ठीक? Itself. So this is the real conditions. So what function we have to take? We have to take a function whose periodicity depends on the number which we want to factor, like this. So this is the restriction. So Now, okay. So Shore said, Shore, the very important contribution from the Shore side. They have selected one such a function, and that one such a function which completed all that requirement is a modulo function. So the modulo function, they have suggested that this function a ki power x mod n. They have chosen such a function. Okay. What is this n? We have to factorize. Okay. And this x is a random variable, means depending upon this function value depends. Okay. And this n is a uh, the number which we have to factorize. So Shore has given this has chosen this, not we should say given, has chosen this function among uh, all the periodic functions. So they have chosen that function. Okay, maybe they will be experimenting a lot of functions. So they have come around. They have made it this criteria, and that's why they have chosen. So it depends on that shows. So, but the final thing is that they have chosen this function, which is satisfying all the criteria. So that means why it is satisfying all the criteria. So what is A? A is a anything which is less than n. A is anything. On the first side, I will say this, but when we will proceed further, we will import some of the restrictions also. So what is A? A is anything which is less than n. Okay. So suppose we have to find the factorization of 35. So we have to choose A which is less than 35. That's it. Okay. So this is the function A ki power x mod n. Okay. Another restriction we will impose on it when we will go on the Shore's algorithm, main Shore algorithm. But here I am telling you this is the periodic function. This periodic function A ki power x mod n. Suppose we are taking a less than 35. So suppose we are taking as less than 35. Suppose we are taking 17. Then this function makes a form like that: 17 to power x and mod 35. This is a modulo function. Okay. Now, what it means, as for now, it is looking like a pure mathematical teaching, but no, this is not a pure mathematical. Based on that, the horse shows idea is there. Okay. So I'm coming to that. Yes. So let me explain further. So suppose now we have formed a function. That function is 70 to power x, and there is mod 35. Okay. So how to solve this? Now everybody knows that. Uh, suppose we are finding this x and 70 to power x mod 35. So this the answer of these things are remainder. Okay. The answer is a remainder. So suppose we are putting x to the power 1. So there is 17 divided by 35. What the remainder we will get? It is not able to divisible. So remainder only we are getting 17. If we are putting x is equal to 2, we are getting that is x is equal to 2. So 17 into 17 by 35. We will get the remainder. We are not calculating. We will get the things right here. Okay. So like that. So like that we have to calculate. And when we are calculating these ones, okay. Actually, I should take a smaller level example so that it will get a clear sight. But okay. Uh, 17. Then after then some remainder will be there. After x to the power 3, some remainder will be there. Okay. And at some value of x, there will be a some remainder which will come like 17. Okay, at some value which will come like 17. So suppose x is equal to 7. Suppose, okay, not exactly I'm sure, but suppose x is equal to 7, it's coming like this, 7 to 17. So that means its periodicity will become r is equal to 7. Okay, so this periodicity is 7. Now, see there. This periodicity depends on, this 7 depends on 35. Why? Because we are dividing everywhere by 35. If we are changing this and we are changing this, suppose we are taking 30, then we have to divide by 30. Then here the periodicity will come something else, right? So the periodicity will be something else. That means the different periodicity R1, there will be a different periodicity. So when we are changing n, we are changing the periodicity. Okay. So this this R and N are in relationship. Okay. So that is the main punchline of this taking this modulo function. Okay. So a lot of people are complaining about this. Then why we are taking this modulo function? Okay. Now, so in this way, we are taking this modulo function and we are reducing the problem of factorization to finding the period finding problem. Okay. So we are reducing this thing. And why to choose this modulo function? Because it's a periodic. And another restriction, it's not the only and only, it's not the periodic. Even then, furthermore, it is having a relation, its periodicity related to the main factorization number. Okay, that depends on capital N. Okay, so this function is always periodic. The same things I have explained you. Okay, from this period we can compute the factor of N. Okay, so this is the very punchline in it. So okay, 1 minute. So this is the short overall problem has converted now to the periodicity problem. So what happens when we will compute the periodicity? Now the problem is not completed. That okay, we have evaluated the periodicity. Suppose we have evaluated the periodicity. Suppose the periodicity is coming like R is equal to 4. Okay. Suppose, for example. Now, when the periodicity is coming out as R is equal to 4, okay. Now, what we have to do? So, what is this QFT part? Because every teacher, what they are teaching, so they know that this we are applying a QFT, the quantum Fourier transform to this function now. Okay. So this I also want to go to the depth of this detail. Why we need this QFT? Why we need this QFT? Okay. So for that problem, now first I will describe what the shore, why the shore is wanted to reduce that problem in the periodic problem. Okay. So because they want 1 minute. Yeah. The shore want that just compute the periodicity and the periodicity computation. So see the methodology. For computing this periodicity, we have to put x is equal to 1, x is equal to 2, x is equal to 3, up to the power x is equal to n. This we have to do, okay, for compute the periodicity, right? So this is the same thing what we were discussing yesterday in the juice algorithm. So classically this thing is the hit and trial. When we are solving this problem in the classical, we have to see the x is equal to 1, we have to see the result. Our classical algorithm, it only can do this. We have to put x equal to 1, see the result, x is equal to 2, see the result, x is equal to 3, see the result, till x is equal to till the periodicity is coming. Okay. So the small label, it is coming like I'm taking the example of x to the power a, x is equal to 8, 9, periodicity 8, 9, 11, 14, like that. But what will, when the periodicity will come like this, suppose periodicity is like 93, periodicity is like 9456. This is the periodicity. Then so much time we have to put all these things, all these inputs. So the same thing. So now we are not benefited by this converting this problem into the periodic problem. Okay. So same thing we are doing in the classical also. We are putting one by one values and we are finding the solutions. So there is no such difference. Now the difference lies when we are coming on the quantum methodology. So when we are coming to the quantum methodology, so what is the difference it will make? Yeah, the same basic difference. What we are doing here in the that what we are doing, x1, x2, we are putting one by one in the classical, x3, x4, we are putting one by one. But what is the capacity of the quantum? That is supremacy of the quantum. So this is the special attribute of this quantum computation, that all the input values we can have in the form of superposition. This is a special, very special attribute of this quantum computing. So we are putting all the input values in a one shot. Okay. So that is a one step and everything is entered. So this is parallel loading. This is called parallel loading, what we have conversed yesterday. There is a quantum parallelism is there, and to achieve that quantum parallelism, we need a Hadamard gate. That's it. So that means, one thing the student are asking that if there is a 10 inputs, and then it will save only 1 by 10th time by inputting 1. So but this method is same, either the inputs is 10 or 100 or 1000 or 10,000 inputs are there. It will implement, or it will enter all the inputs into the circuits in one slot. Okay, in one shot. Okay, that means it will take a one step only to input all the things to make it superposition state. Okay, so there is a 10,000 inputs and 10 lakhs inputs, then it will take a one step only. Okay, yes. So, there the beauty of the quantum computation or methodology of the quantum computation lies that we have to enter the same beauty was yesterday, that with the same attribute we are able to solve that constant or function balance problem. We are able to recognize the function is constant or balance. With the same beauty of this attribution, we now are able to inputting all the x1 values in a one shot. When we are inputting in a one shot, that means this is the key. This is the key. Just input and find the periodicity. If we are inputting every values from x to 1 to 100, then it means we can find the numbers where the periodicity is starting and recycling. So suppose, for example, I'm taking suppose 24932, 493, like that. So here there is a periodicity. When we are inputting everything simultaneously, and we will see the output for that. Yeah, of course we have to apply. It will not give like that. This is a superposition. Now we have to apply another circuit. The another circuit we will talk about, that is the oracle. Okay, that is the oracle. We have to apply this oracle. The circuit of the oracle will be completely different. So we have to apply the oracle at here, and that oracle will compute these things. But what we will require, this oracle we can also supply to the classical. But what the beauty is there, difference is there, this parallel inputting. So everywhere, whatever the algorithm, what are the applications algorithm you will hear, you will find there is a parallel input which makes it special. And because of that, it is able to calculate the faster. Otherwise, on the other level, it will be same as a classical. So this oracle we can find, we are forming it. We are forming the oracles in the classical algorithm also. Okay. So, this is the thing that okay, yeah, now. So now come to this problem. So what we are doing, we are finding the problem of periodic, sorry, period. So now we are able to find the period R. Okay. So when we are able to find the period R, that means everything is done. So next step I will tell you some later. But now I am telling that we are finding if we are finding in a quantum way, then we have to keep in one mind one thing, that quantum is giving the advantages of inputting all the things in a one shot. But at the same time, it is also giving the problem how we can resolve that superposition waves. Okay, and then simultaneously it is giving the same problem how we have to resolve that mixed signal into the correct answer. Right, what is the problem here? So understand what is the problem here. The problem here is 1 minute, let me see on the chat box, is there anything? Okay, you can post the queries in the chat box. Sometimes I'm seeing it here. Okay, so here. Hmm. So, yeah, we were at this step that we have formed the superposition state, and that superposition state we are passing through the oracle. That's it. We are passing through the oracle. Oracle is a some type of function that is a combined matrix function. Okay. Then after the oracle, we are left with the superposition. Okay, this is superposition one. So now after the oracle, the form of the superposition will change. So maybe it is inputting in this form like this at here, but maybe we will get form like this. Okay, no problem. Yeah, because after the oracle, the form will change, but the form will change. It will remain mixed. All the inputs. So all the inputs in the intermixing, all the this is also mixed state. Now, how to find the solution? We are actually I have not yeah deal this problem conventionally. All the teachers are dealing. I just involving the conceptual things. Okay, because that needs to be added in the teachers. So yeah, now this problem remains the same. There is a mixed state of this. When there is a mixed state, now how to find the periodicity in this mixed state? Okay, the periodicity R is equal to 4, suppose we are getting, then this 4 periodicity, how to find it? We can find it. Yes, we can find it by measuring. Simple solution. We can find it by measuring. Okay. So suppose 2, 4, 6, I'm taking example, and 8, and after that again 2, 4, 6, 8. It's coming like this. So all the mixed state, this is a mixed cat 2, cat 4, cat 6, cat 8. This is a mixed state we are having now. This one. Okay. This is the mixed state we are having it here. Now, when we will measure, so there is a one problem with the quantum on the measurement of side. So when we are going to measure, then only any one point we will observe. Either this, we should change up 1 minute color, or this, or this, or this. Any one point we are able to observe. So that means we are having a 2, 4, 6, 8, then 2, 4, 6, 8. We can find the periodicity if we are at least 5 inputs we want, 5 outputs we want. This, and this. Okay. If suppose we are saying we have this 6, then how we can say what is the periodicity? After measurement, after measurement, we are left with one of the state. All the states will collapse. This is the different states. All the states will collapse. Then when all the states will be collapsed, we are left with any of the one state. Suppose we are left with this 4 states. Suppose we are left with this 4 state. Then how to find the periodicity? Periodicity only we can find when we are having 2, 4, 6. If we are observing everything simultaneously, 2, 4, 6, 8, then we are observing 2. Oh yeah, the periodicity is 4. But when we are finding one number, we cannot say about that. So it is uncertain. Okay. So that is the problem. That is the problem. We need additional arrangements to find it or to manipulate this problem into the final output. So how to do this? How to do this? This we can do by transformation. That is, we are having another tools that is called Laplace transformation, Fourier transformation. So all the tools we are having. So we have to transform this one. So how to transform that? So this 2, 4, 6, 8, then 2, 4, 6, 8. So transformation means we have to do the transformation, but we are restricted that we cannot measure everything here. So we cannot measure all the 5 states simultaneously. No, that is a restriction. So this restriction can be overcome. This can be overcome when we will do the some transformation. That transformation is a Fourier transformation. And what is the work of the Fourier transformation? The transformation Fourier is used to transform from one frame of reference to another frame of reference. So there is a parametric changes. Parametric changes means to say that uh, suppose suppose on the space there is a x, Suppose on the space, we can change the basis to time, t. Okay. So in the communication, EC, in the communication, this is used very, very rare or very frequently, that the space problems are reduced to the time domain. The domain problems are reduced to the space problem for the communication signals, right? So this Fourier transform we can apply here. Okay. So and when we will apply this Fourier transform, so when we will apply this Fourier transform, that is QFT. When we will apply this Fourier transform, what will happen? Suppose now I will deal with the waveform. Suppose this is a waveform. This is a waveform, and on this axis, on this y-axis, there is a count of this amplitude. Okay, how much amplitude is there? There is a count on the y-axis. Okay, on the x-axis, there is a count of distance. Okay, or we can say periodicities. Okay, x is equal to 1, 2, 3, 4, 5, like that. So this is x is equal to 1. This is suppose x is equal to 2. This is x is equal to 3. And this is x is equal to 4. Okay, but the problem here is the same problem I'm describing in a graphical way now. Okay, so some person can understand in that way, some person can understand in that way. So suppose when we are going to measure, only the one point we will capture. Measure means capturing a photo. Okay, in the live video we are capturing a photo. That means we cannot have the full video. When we are capturing, that means when we are measuring, we are finding all the states collapsed. That is, suppose we are measuring at this point. Suppose at this point we are measuring. So when we are measuring at this point, we are left with this value of x only. This value of x only. Okay. So when we are left with this value of x, so we cannot find the periodicity. Okay. So what we are doing, we just converting. There is a one solution for this. This axis is creating a problem for us, right? This axis is creating a problem for us. Why? Because this axis we are representing the different values of x. If anyhow we can change the basis of this axis, that is not to the x, we can change the basis to the time domain or frequency domain. Okay. So when we will change this domain to the frequency domain, so that frequency domain here, if we are representing the frequency instead of time, now I'm changing everything here. So instead of time, if we are going to change it on the frequency domain, so if we are catching this wave, suppose this is a frequency f1, this is a frequency f2, this is a frequency f3. So when we are capturing the image at this point, that means we are having a left with the frequency f1 now. Now we are coming with the frequency f1, and we know that frequency is how much cycles coming per second. Okay, so that means this frequency itself comprises the information of periodicity. Okay, periodicity means time period, and we know that frequency and time period are interrelated, inversely proportional, like that in the wave. So if we are converting this base to the frequency, so when we are capturing the one point, even on that one point, we are having this frequency. From that frequency, we can find out the periodicity. Okay, that is R. Okay, so to convert that space, we need to apply the Fourier transformation. Okay, so that's why we are applying the Fourier transformation right here. Okay, and when we are applying the Fourier transformation, then we are left with the periodicity, and when the periodicity will be there, we can find out further. Everybody knows, I think, that when we are having, okay, if not known, then I'm writing this. The first step is to choose the value of a, okay, such that now I'm imposing the constant which I left there for the sake of convenience. That choose a such that, suppose we are finding, the aim is that we are finding number n, factor of number n. So we choose A such that two things. A should be less than n, and second thing, the GCD of A and n should come out to be 1. Okay. So all these things are mathematical. You can understand very well. Okay. It's a formal things that I'm providing here in the 2 minutes. So first, A belongings to such that A is less than n. A is less than n. Second, GCD of A and n come out to be 1. So whatever we are choosing A, I will give you one example for it also. Whatever we are choosing A, the common factor that come out will be only and only 1. So there is only a one common factor, other than there should be no common factor. Okay. Then the second requirement, what we have to do, we have to form a function. So whatever we are choosing, we have to form a function a to the power x mod n. Mod n means whatever the function we have to do the factorization, what the number we have to do factorization, right? And then find the periodicity. Periodicity, mathematically, we can find very easily. We can form the table x, and this is x a to the power x by n. That is remainder table. Okay. Put the value of 1, find the remainder. Put the value of 2, find the remainder. Like that, we can find from this table, we can find the periodicity r. Okay. So when we will find the periodicity, the fourth step is that after the periodicity, we have to form this a to the power r by 2 minus 1. Sorry, a to the power r by 2. We have to find this factor a to the power r by 2 when we're finding the periodicity r. So yeah, there is a one restriction that this periodicity should be even. Why this? This I will tell you later. A by r, a to the power r by 2. Then what is the number we are getting a to the power r by 2? Then subtract the number by 1 and add the number by 1. We will left with these two factorizations. These are the two prime factorizations what we are aiming. Okay. So that is a mathematical way to solve that problem. Let's take one example, numerical example for this. Then it will be more clear. Suppose n is equal to, we are having 35. Okay. So n is equal to 35. We have to choose such a first step. We have to choose, suppose we are choosing a is equal to 2. Why I'm choosing? Because 2, it will give you ease of calculation at here. We are restricted by the time. So a is equal to 2. That means it will give you, now we are forming, of course, it is satisfying one criteria, 2 is less than 35. Another criteria is that GCD, GCD of 2 and 35. So it will only come 1. Okay, there is no other value which will divisible. That is divisible to 2 and 35 also. Okay, so only there is a 1. Okay, yeah, it's satisfying both the criteria. Now, what we have to do mathematically, we have to do like this. There is x, there is a is equal to 2, so there is a 2 to the power x. Okay, divided by n means 35. Okay, here we will get a remainder. So just from this table, so put the x, a value of x is equal to 1. It will be 2 to the power 1, 2 by 35. We are left with 35. Okay, x is equal to 2. We are left with 4 by 35. We are left with 35. Like that. So we will continue 3. We will continue 2 to the power 3. 2 to the power 3 is 8 by 35. It will give you 35. It will continue, or I think 8 to the 16 to the 24, uh, 16 to the 32. Then actually I'm calculating this thing. This is increasing by the power of 2. So x is equal to 4. It will be 16. X is equal to 5. It will be 32, like that. Suppose, I think I have remembered this example. Suppose x is equal to 12. So x is equal to 12, it will again return to the same value, I think. Okay. At x is equal to 12, you can check it. Okay. Otherwise, there is something around near about x is equal to 11 or 12. Okay. I have given this example frequently. That's why I'm remembering this x is equal to 12. Okay. So it will return to the same value at here. And why it is happening so? Why the modular function is a periodic function? Because suppose if you are dividing something by 7, suppose any function, suppose anything, suppose x or suppose y. Suppose we are dividing y by 7. So when we will dividing y by 7, so always this is a very basic mathematics, nothing in it yet, but I'm telling, okay, so that you can get it. Why it is a periodic? Because whenever we are finding a remainder, so that means it is a compulsory thing. Whatever we are doing this division, so there should be only and only less than 7 remainder we will have, right? So the remainder means when suppose we are finding 19, so that means 7, 19, 2 the 14, and here is there is a difference of 5. This difference or this remainder should be less than 7. Otherwise, if it is not less than 7, if it is suppose if it is 8, okay, it's a very basic mathematics, okay, but yet I am telling, suppose it is 8, remainder is 8, then what will happen? 24. Suppose 25 I'm taking, okay, then 4 or 5 9. Suppose remainder 9 I'm taking, then it is wrong. Nobody can go in this method. So you will certainly say, obvious, very obviously you will say why, yeah, there is like this, okay. So there is a 21. So you will left with 3. So whatever the remainder you are left, the remainder is always less than this number, right? So that means you are left only 7 reminders. After that, you will repeat it. You will repeat the reminders value. So that's why here the periodicity lies it here. Okay, that's why the model on n remainder problem we are taking as a function. Okay, so yeah, okay, let's move ahead. We have got mm, okay. So we have got periodicity that is x is equal to 12. So when we have got the periodicity that is r is equal to 12, we have got that means now we have to calculate r by 2. That r by 2 is 6. Okay. So this is 2 to the power. So this is a key power r minus 1. This is the r by 2. So a 2 to the power r by 2 means 6, 2 to the power 6 and 2 to the power 6. This is we are getting 2 to the power 3 and 2 to the power 4. This and there is a I think 2 to the power 3 is 8, then 4 is 16, then 5 is 32, and 6 is 64. We are left with the 64. Okay. Then 64 minus 1, 63, and 64 plus 1, 65. So there may be two conditions. Either we are getting directly these things as a factor, or if we are getting these numbers greater than the 35, then we have to take the GCD. GCD for 35 and this 63. Okay, we have to take the GCD of 35 and this 65. Okay, so this GCD I think it will come out by 5. This GCD it will come by 7. Okay, then these 7 and 5 will be the factors. These are the mathematical way to do these things, short algorithm. Okay, so now what about circuit? The circuit now I think I have cleared every steps. So circuit you will have a no problem I think. So what the circuit will be there? There will be a Hadamard gates. You will apply at the every input. So this Hadamard gate, what it will do? This Hadamard gate will convert everything into the superposition states. Superposition states. And after this superposition state, what we have to do? We have to apply some oracle UF. For this oracle, how to design this oracle? We have to keep in mind this have to design for the a to the power x mod n. This oracle should compute a to the power x mod n. Only that one. Okay. So that is the work of the designer. And now that yeah, of course that is having a circuit. Okay. Then what we have to do? The main part is that now we are left with the periodicity R, but that in the form of superposition. So what we have to do? We have to do the QFT, Fourier quantum Fourier transform. Then we are left with the frequency. Okay, that will give the answer. That will be a circuit of this. Okay, so this is the factorization problem. Okay, and this factorization problem now it's creating a boom in the classical industries, classical computer industry. So when this quantum computation will come and this quantum hardware will come, then our encryptions will no longer be remain safe. Okay, because what the encryptions are there? Encryptions are there now. They are not able to find P and Q, two prime numbers of the same 500 digits number. Or they are going up to 1200 digit number at randomly, and they are choosing this number at randomly. Or and if you can go onto the website of any such type of company, they are releasing these keys, they are releasing these things, that we have taken this 1200 number. Okay, take it this number and hack this one. They are opening, they are giving the open challenge. Nobody can hack this number. Like, hack this number means nobody can reversely trace this P and Q, and that's why they are safe, the encryptions are safe. Okay. So, but when this quantum computation will come, then this encryption problem will no longer be as safe. That is the drawback for this. So we have to move to the another level of securities then. Okay, because somewhere, suppose if there is a two or three systems there in India of the quantum computation, suppose that every startups are making, then this simulation will break the classical computer's encryption. They are used to break the classical computer's encryption. So we have to add the another level of security for the this to save ourselves. Okay, now now we can move towards some cascade activities. Hmm. So okay, so in a 2 minutes, let me prepare this things. In a 2 minute, I am sharing this cascade activities. We will move our program from where we are left yesterday in the cascade coding.
Vipul sir, what was an issue? Your screen is not visible and also you're on mute.
No, no, nothing is the issue. Just I'm preparing my cascade this environment. Okay,
Okay,
just
sir, no problem.
oh, yeah, just for 1 minute, I'm sharing everything.
Yeah, yeah, sure.
Yes, I'm sharing. So the screens are shared. Okay. So, yeah. So we are beginning this quantum programming. We have left. I'm just first importing. We have to import everything. We have discussed these things. Yes. So the simulator is ready now. Okay. So now we have to do what we have to do. This yesterday programming we have done for the for quantum circuit. That was the word used to build the circuit programmably. Histogram, then air simulator. That was act as a classical simulator of the quantum computer. Okay. So we have imported these quantum circuits in the Hadamard gate, and then we have measured all the values in the Cliff-Ward style. Okay. Now we are moving ahead, and after the shots, 100 shots we have, 1,000 shots we have run there. Now we are creating an entanglement circuit. So for that we are writing a one code at here. So this code, mm, mm, yes. So so we have written one code as here. What the code was here. So that is we try to create an entanglement, and this entanglement is the most iconic quantum phenomena. So what we did it, we had applied a Hadamard gate to the qubit zero, and we know that Hadamard gate, when we are applying to the zero, creates a superposition state that is a positive state, cat positive, and then applying a C naught with a qubit zero also as a control and qubit one as a target. So you are able to see that the resultant state should be like this: zero zero cat zero zero, this cat one one plus root two that we are having theoretically. So this state has a perfect correlation with the qubit behave as a single combined system. Uh, I think all of you are able to see this. Yeah. Okay. So what we are doing nothing. Quantum circuits, we are calling this word, and this QC2 is the input values. Then Hadamard gate we are recalling in this. Then we are calling up CNOT gate. CNOT gate representation is CX, that is 01. That we have to specify the inputs also, control 0 and the target 1, like that. Then there is a command for the measurement. So we have given all the commands, and this I was talking yesterday. This style I have quoted so that warning will not coming here. If I will not quote this style, the warning will come. So this is the circuit we have created. Now we have to run this program also. So for that, run that entanglement. First, we have to give the command for the backend that run, and we have to also specify how much shots we have to run these circuits. So yesterday also we have seen that. So the histogram I have run here. So this histogram is giving the value like this. So there is a 00, there is a 11. So 00, so this 00, and having the 548 shots, this 11 having the 476 shots. Okay. So that is giving a perfect correlation between the entanglement state. So observe this result carefully. You will notice that output are almost exclusively. Okay, that is 0, 0 and 1, 1. And exclusive means to say that 0, 1 and 1, 0 will never appear at here. Just note down, note this punch. That 0, 1 and 1, 0 will never appear here. And this is a signature of entanglement. Entanglement means whatever the rule is there, rule should follow. So the rule is there, it should follow the control and target same. So the 0, 0, then 0, 0, 1, 1 means 1, 1. Okay. So next we are demonstrating this X side and Hadamard, Z gate and that Hadamard. So the screen is visible.
Yes, sir, it is visible, sir.
Okay, okay. So this Qiskit window is open to you now.
Skip window, it is not open, I guess, sir.
So what screen, ma'am? Are you able to see?
The count, the chat which is showing with that pie
Graph.
chart will graph, yeah, is correct.
Okay, okay, okay. Fine, fine, fine. Okay, fine. No worry. So next command I am giving to this. So here I have given all the commands that in a one shot, that just circuit and as well as measurement. So this is the circuit. So this X gate we have taken as an input, and then we are measuring this circuit. Then after the measurement, just see the histogram. So this output 1 is coming to a, we are giving this output 0. So that means by default, the outputs, by default, the inputs are set it in the 0 state. Okay. So the output will come to 0. Oh, sorry, 1. Okay. So that output 1, we are running 512 shots. Then the output is coming 1. So that signifies the clear simulator is working fine or circuit is working fine. So now we will run Z gate. For the Z gate, we are having the hmm, output like this. See the histogram. There is a Z gate. In the histogram, we will get of 0 for the 0. Okay. Now, phase change are invisible in the measurement. That's why the output remains 0. You will be wondering that why the 0, 0. No, no. So the phase change is invisible because we are having an input 0, output is also 0. That's why. Suppose now, see, this we are importing Hadamard gate, applying in the Z. Hadamard gate applying in the Z. Then we are measuring all the things. So Hadamard gate, Z and Z. And we are seeing, so it's very necessary in the initial level, it's very necessary to run this command along with the circuit. This command. Display this and get counts. Okay. By seeing the histogram. So when you are observing the histogram, so it is giving you this one value to the this 512 counts. So you can observe, you can verify when you are inputting 0, whatever what should you get. Okay, how to verify that? When you are inputting 0, if you are inputting 0 here, what you will get a positive state. When you are inputting positive state here, So this Z will apply on the both the states of positive. Then just do the negative according to the Z2 table. Then apply this, the whatever the inputs we are getting, apply this to Hata market. That you can apply logically. Then measurement. This is the measurement. Hmm. So these are the at random circuits. I think now we have to move with the. So we have to now we will create some algorithm circuits. So yesterday we have discussed the Deuce algorithm. So suppose we are now creating that circuit, but this demonstration will prove you how this implementation in practice. Explore the creating qubits, applying gates, simulating the circuits, and visualizing the measurement in terms of histogram. Okay. So that is especially the software layer that brings quantum circuit to the life. From here, we can scale up to the algorithm like QFT and Grover and Shor. So we are moving towards that algorithm. That algorithm, we need to do a circuit for that algorithm also. Hmm. So uh, in the algorithm, we need to check that first the oracle needs to be designed. So the unknown function fx in the deuce, suppose we are talking about the deuce, so the unknown function fx that is represented as a quantum oracle, right? So oracle we have talked about a lot yesterday. It's nothing but a small quantum circuit, internal circuit. So designer will know that, the customers they are not knowing this, okay, how the fx behaves. So if we are uh, left with the fx, then fx can have a constant or balanced value. So we have the mathematical operation for that. So now we are first defining quantum oracle. So the quantum oracle, 1 minute. Yes. We have defined the oracle. Then we have to input the values, the zero value and one value. Okay. And then 0, 1. So for the function fx, the output equals to the input. That is the deuce representation of this uses a C naught gate. So we set qubit 0 as a control, qubit 1 as a target in the circuits. This means if the input is 1, flip the output. That correctly represents a balance function. So now I am having the code in it that will flip the first qubit and apply the same C naught gate. Now applying the, now there is a working. So we create a circuit with the two qubits and one classical bits. The first qubit hold the input, and the second qubit is the work qubit used by this oracle. And now we are initializing the second qubit. So it requires the second qubit to begin in the state 1. That's we set it here. Now applying the Hadamard gate. What is this? QC is not defined. 1 minute. And how this is now? Okay, 1 minute. Hmm. Hmm. Oracle को constant करना है. Okay. Hmm. Now it is defined. Hmm. Now, now I think we will do a Hadamard gate. Like this. We have to define this Oracle constant also, I think, yes. Hmm. Hmm. Yeah, it's run. Then Yes. So here is the algorithm that runs. Now we have to measure. Hmm. Yes. So it's a circuit for the algorithm, juice algorithm. So Hadamard gate we are applying here, and there is a X oracle we are applying it here. And 1 minute. Let me. Hmm. One more time. Then hmm, yes. Hmm. Let us define this oracle right here. Hmm. Hmm. Yes. So that is defined by another oracle. So both all the circuits we have implemented here. If we want to check, yes. So that is Q0, Q0 and Q1. That is applying on the first Hadamard gates. So that is some demonstration how the this algorithm can work. And in the next day, we will demonstrate the Shor's algorithm, how it will work, and we'll talk about some Grover's algorithm and some hardware section. So now I'm lefting over this theory session. So is there a question and answers and queries? You can put up on your chat box. Hmm. So any questions or anything? So I'm waiting for the chat box. Yes, Rashmi. Now the voice is audible. Yeah. So okay. So we are winding the session. So hand it over to Sushmita ma'am. Hello.
Yeah, sure, sir. Yeah, I'm there,
Yeah.
sir. Thank you so much.
Yeah. Okay. Okay.
Yeah, so dear faculty members, like you all are asking about the materials which is already uploaded in LMS dashboard. I request please check that. So all the complete 3 days of PPT which has been sir taught in the session, that is all uploaded in LMS.
Hmm.
And some are asking for previous day attendance which can't be shared. Yeah, please, sir, you can talk. Okay, we have 5 more minutes. If any questions or queries, you can just drop in a chat so that for the technical thing, the sir will answer, or any related to LMS, I will answer. We have 5 more minutes. You can drop a chat, like if any questions are
Ah,
there.
yes, yes, yes. Two questions I have received here. Yeah, could you share the resources for the yeah implement the coding? Yeah, yeah, yeah. Okay, we will share the resources for that. Okay, so the resources you can find in the IBM Qiskit modules. So they are having the authentic website. So there you can find the all the this Qiskit vocabulary. How to execute the mod function. Okay, to execute the mod function, we need to create a Oracle. Oracle means a personal circuit that we will implement tomorrow. Okay, okay. Any more query? Anything you want to ask from this Qiskit program or this algorithm, Shor's algorithm? Hmm. 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 Okay, thank you. Thank you all. Thanks. Anything you want to clear your queries? Anything doubt? Yeah, I generally didn't involve any general things which are running in every YouTube lectures. Hmm, okay, no worry. So Sushmita ma'am can share. Thanks for all these comments. Is there any security to be maintained in quantum computing, sir? In the security issue, there is a lot more about the drawbacks. PPTs, I think you can download from the LMS itself. And yes,
Yeah, yes.
Yeah, in the security issue, uh, so as soon as the new technologies are coming, they are coming with the both the sides, right? The speed up and the security issue. For the security layer, we have to create the security layer as per the quantum point of view. Yeah, there is a security issue for the classical computers. Yeah, the small dragons are the classical computers, but the biggest dragon will be the quantum. So it will have, yes, because it can break everything. Okay. Thank you. Thank you. Thank you all for this nice comments. Still any doubt? Anything else? Anything you want to include in the next session regarding this recording? I think Sushmita ma'am can tell you. All the lectures they are, I think, uploaded on the YouTube. Yes, yes, on the YouTube, I think.
Yeah, the recordings which is visible on YouTube as well, and also which is already all the recordings materials has been uploaded in LMS dashboards.
Hmm.
Okay, sir. If you do, or
Okay.
like if we don't have any questions, so we can wind up for the day. We'll meet
Yes,
again
yes.
by tomorrow.
Yes, okay, okay. We can wind up the session. Then we will meet in the tomorrow with the
Yeah,
more examples.
yeah,
Okay.
sure, sir. Thank you, sir. Thank you so much.
Oh, thanks.
Yes, so dear faculty members, as already informed, all the materials and recordings which is already visible on dashboard, kindly go through there. And about the attendance, which is already shared. And some are asking for the mail ID and the contact number of the trainer. So we are not supposed to share any of the personal details. I request please not to ask any of the personal details of a trainer, not even a LinkedIn ID. If any questions or query, you can drop a mail to edl@xlr.com. Will help you there. The attendance link, which is already shared, like some are asking for it. Let me share it once again. Okay, thank you all. I have shared the attendance link once again. Yeah, so we will wind up for the day. Thank you all. Thank you for joining.